This tape has two primary objectives. The first objective is rather obvious. That is to teach you the properties of determinants. The second property, though, or the second objective, is just as important. The second objective is to teach you more about the technique of proof. I'm going to illustrate two proofs in today's tape. One proof is the beat it to death method. In other words, expand it out, make the change, and then collapse it back. That method of proof will be used a great deal throughout the course. The second proof involves what you have to do if you are proving an if and only if statement. So anytime you're proving a theorem that says if and only if, you're going to have to do two parts. I will illustrate that in today's tape. For the following properties, assume that A and B are square matrices of order n, and that C is a scalar. Now, say we have a square matrix of order n. That means that n rows, n columns. The first property is that the determinant of the product AB is equal to the determinant of A times the determinant of B. So if I multiply two matrices using matrix multiplication and determine the determinant, I will get the same result as I would if I do the determinants before multiplying. And then multiply the two determinants together. The determinant of a scalar times a matrix CA is equal to C to the nth power, where n is the order, times the determinant of matrix A. So if I factor out a C from the entire matrix, then I would need to, and then evaluate the determinant of the matrix that's left, I need to multiply Cn times the value of that determinant to get the determinant of the original matrix. The determinant of A inverse is 1 over the determinant of A. The determinant of A inverse is 1 over the determinant of A. The determinant of A transpose is the same as the determinant of A. Some of the proofs are in the book. Some will be left as exercises for you. I'm going to prove property 2 here on the tape. Now with property 2, I'm going to show you how you can expand something out and then collapse it back. So I put the type proofs that we're going to do now in beat it to death area. In other words, there's nothing subtle about it. You simply analyze what's going on and write it out in all the detail. So proof of 2. Let's start with CA. So I'll let A be the matrix, A11, A12, A13 out to A1n, A21, A22, and so forth. And we have an n row, n column matrix. So it's n by n square matrix, whereas the little a's are each of the entries. So I have CA. Well, we know that for the matrix we multiply C by every element. So if I multiply C by every element, I get CA11, CA12, CA13, CA1n, and so forth. So now we want to do the determinant of CA. Now this is a matrix CA, so we're going to do the determinant of matrix CA. Well, in the last tape, we had a property that said if we multiply through a matrix, then if we multiply a row of determinant by a constant, then A, matrix A, the one I started with, would be the matrix B, the one I get, divided by the constant. So I'm going to factor out 1 over C. So I'm going to multiply through by 1 over C. So I'm going to multiply row 1 by 1 over C. If I multiply by 1 over C, then this would equal to the determinant of that result divided by 1 over C, which would be multiplied by C. So this is going to be C times the matrix A11, A12, A13, A1n, and so forth. So I factored a C from the first row. Now actually what I did from here to here, I multiplied by 1 over C. So then I would need to divide matrix B by C, divide matrix B by 1 over C, which is the same as multiplying by C. Now I'm going to do the same thing to row 2. So for row 2, I'm going to multiply by 1 over C. So then that would be the same as dividing that determinant by 1 over C. Dividing by 1 over C would be the same as multiplying by another C. So I already had the 1C. I'm multiplying by another C. Well, I'm going to continue doing the same thing. So I've taken care of 2 rows. And when I take care of 3 rows, it would be C, C, C. When I take care of n rows, it would be C to the n times the matrix determinant of A. Well, that's what we wanted to prove. We wanted to prove that the determinant of CA was C to the n times the determinant of A, which is what we have. Now this is an extremely important property of determinants that we'll be using throughout the course. A square matrix A is invertible if and only if the determinant of A is not equal to 0. So a square matrix A is invertible if and only if the determinant of A is not equal to 0. Now, invertible means that it has an inverse, which means that it's not singular. So you need to get all those terms in mind. But it has an inverse if and only if the determinant of A is not 0. Well, since the process of finding the inverse is somewhat complicated, it would be nice to know if there's any point starting. So if the determinant of A is not 0, then we can find the inverse. Now, this is important in its own right, but I also want to illustrate if and only if. Anytime you have the if and only if, you've got to do 2 parts of the theorem. So for proof, we must prove 2 things. The first, we must prove that if A is invertible, then the determinant of A is not equal to 0. So I must do it frontward. If A is invertible, then the determinant of A is not 0. Now, if and only if means I also got to do it the other way. If the determinant of A is not 0, then A is invertible. So anytime you see if and only if in a statement, it means that you must prove it both ways. If A is invertible, then determinant of A is 0, is not 0. If the determinant of A is not 0, then A is invertible. So that's one thing to note about if and only if. One more time. A, if and only if B, automatically means two things. It means if A, then B, and if B, then A. So to prove an if and only if statement, you have to prove both of these. Well, let's look at if A is invertible, then the determinant of A is not 0, and go through that. So part 1. If A is invertible, that implies that A has an inverse. And if A has an inverse, I know that A times A inverse is the identity matrix. Now by property 1, we know that the determinant of A inverse is the same as the determinant of A times the determinant of A inverse, because the determinant of AB is the same as the determinant of A times the determinant of B. So I simply took the inverse of both sides. I simply took the determinant of both sides. So the determinant of A inverse is the determinant of I, but the determinant of A inverse is the determinant of A times the determinant of A inverse, using the theorem that the determinant of AB is determinant of A times determinant of B. Now we know that the determinant of the identity matrix is 1. Now if you see the identity matrix is going to have 1s along the diagonal and 0s elsewhere. So then it's triangular, so all you do is multiply the diagonal, so it will be 1. Well, this proves that A is not 0, because if the determinant of A were 0, 0 times something would not be 1. If the determinant of A were 0, then 0 times A inverse would be 0, but it is 1. So there is no way you can multiply two things to get 1 and one of them be 0. So the determinant of A is definitely not 0. So that proves the first one. If A is invertible, then the determinant of A is not 0. Now we're going to prove the second one. If the determinant of A is not 0, then A is invertible. Determinant of A not equal to 0 implies one can find a matrix B in row echelon form that is row equivalent to A. So if the determinant is not 0, well really whether it's 0 or not, one can find a matrix B in row echelon form that is row equivalent to A. So given any matrix A, I can find a matrix B in row echelon form that is row equivalent to A. Now remember, row echelon form is you have 1s and 0s along the diagonal, 0s all along it, below it, and in reduced row echelon form you've also got 0s above it. Now, if matrix B is equivalent to A, then B is the identity matrix, or B has a row of all zeros. Because remember, that's why I told you about row echelon form. To talk about row echelon form again. So as far as the reduced row echelon form. We'll look at the 3 by 3. Well, to get it row echelon form, what we need to do is have all zeros here. But what I would do is I would just multiply the first by 1, add to the third, by negative 1, add to the third, so it would be 1, 2, 4. And when I 0, 2, 6, negative 1 times 1 is negative 1 plus 1 is 0. Negative 1 times 2 is negative 2 plus 0 is negative 2. And negative 1 times 4 is 4 plus 4 is 0. So what I'm trying to do is get, the ones here. The process is I can do that. I can get all zeros here. I can get zeros everywhere except the diagonal. So what I would do next, it's kind of an automatic process. I would divide the second row by 2, so it would be 1, 2, 4, 0, 1, 3, 0, negative 2, 0. Now I'll fix this. I'll multiply row 2 by negative 2, add to row 1. So leave row 2 the same. Multiply by negative 2. Negative 2 times 0 is 0. 0 plus 1 is 1. Negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 3 is negative 6 plus 4 is 2. Now I'll multiply by 2 and add 3. So 2 times 0 is 0. 0 plus 0 is 0. 2 times 1 is 2. 0. 2 times 3 is 6. 0. 6, I'm sorry. Now I divide by 1, 6, get all ones, then I'll eliminate these. So you can see that when I'm doing this process, one of two things is either going to happen. It's going to be all ones here, or it would be somewhere in which I get zeros. So I can keep row reducing it until I get one of those conditions. So either B is the identity matrix, which was deal, or B has a row of all zeros. One of those things will happen. But B cannot have a row of all zeros, because if it did, then the determinant B would be 0. One of the things you look for a zero determinant is a row or column of zeros, which implies, so if the determinant B was 0, that would imply that the determinant of A was 0, because I got B by row reducing A. And as you row reduce it, if you interchange rows and columns, then you might change the sign. If you add a multiple of a row to another row, you don't change anything. If you multiply by a constant, then you do affect it by the constant, but none of that would create a 0. So if the determinant of B were equal to 0, that would imply the determinant of A is 0, which can't be, because we said the determinant of A is not 0. So we got the contradiction here. So the only condition is that B must be the identity matrix. So if the determinant of A is not 0, we write it in row echelon form, then B must be the identity, which means that A is row equivalent to I and is therefore invertible. It's one of the properties that I gave you a couple lessons ago of equivalent conditions. So we know that I is invertible. A is row equivalent to I, so therefore A would be invertible. we'll use the property that I proved for you to simplify the evaluation of this determinant. So we want to evaluate the determinant 4, 16, 0, 12, negative 8, 8, 16, 20, negative 4. Well, I can factor a 4 out, so using the property I proved, that's going to be c to the n. C is the 4, n is the dimension, so it's 3 by, n is the order, so it's order 3. Since I have a 3 by 3 determinant, so it would be 4 cubed times the determinant of what I would have when I divide out the 4. That would be 1, 4, 0, 4 going to 12, 3, negative 2, 2, 4, 5, negative 1. So by factoring out my constant for 4, raising it to third power, I have much easier numbers to deal with. Now if I multiply row 3 by 2, add to row 2, that would be 4 cubed times 1, 4, 0. I'll leave the 4, 5, negative 1. I'm going to multiply row 3 by 2 and add 2. 4 times 2 is 8. 8 and 3 is 11. 4 times 5 is 20. 20 plus a negative 2 is 18. I'm multiplying row 3 by 2, adding to this one. So I did that wrong. 2 times 4 is 8. 8 and 3 is 11. 2 times 5 is 10. 10 minus 2 is 8. I'm multiplying by 2. 2 times negative 1 is negative 2 plus 2 is 0. So I multiplied row 3 by 2, added to 2. 4 times 2 is 8. 8 and 3 is 11. 5 times 2 is 10. 10 minus 2 is 8. A negative 1 times 2 is negative 2 plus 2 is 0. So now I have all zeros, the zeros in this column, so that would be 4 cubed times, I'm going to expand around the third column, so it would be negative 1. These will be zeros. Negative 1 to the negative 1 to the third row, third column, 3 plus 3 times the cofactor. Well, if I take out third row, third column, I'm left with 1, 4, 11, and 8. So it would be 64. Now negative 1 to 6 is positive 1 times negative 1 times 8 minus 44, which is very easy for you to finish. Determine whether the matrix 2, negative 1, 6, 1, negative 3, 4, 4, negative 2, 12 is singular or not singular. Well, the property I proved for you is if the determinant of 2, negative 1, 6, 1, negative 3, 4, 4, negative 2, 12, if that determinant is equal to 0, then the matrix is singular. Now, of course, if the determinant is not 0, then the matrix is invertible. So if the matrix is 0, then the matrix is not invertible, which means that it is singular, because we proved it if and only if. Well, what's the best way of evaluating this determinant? We have no zeros in it, so what we might want to do is to row reduce so that I have all zeros below the 2 in the first column. So that's probably be the easiest thing to do first. So just leave the first row the same and multiply the first row by 1/2, add -1/2, add to row 2 would probably be the easiest thing to do. I'll get one fraction, that's not too hard to deal with. So we'll multiply row 1 by -1/2, add to row 2. A -1/2 times 2 is a -1, plus 1 is 0. A -1/2 times -1 is a +1/2. A +1/2 minus 3 is a -2.5. A -1/2 times 6 is a -3. -3 plus 4 is 1. Now we'll multiply row 1 by -2, add to row 3. -2 times 2 is -4, plus 4 is 0. -2 times a -1 is +2, plus 2 is 0. A -2 times 6 is -12, plus 12 is 0. Well, I have a row of all zeros, which means that the determinant, if we call that matrix A, is 0, which implies that it is singular. Now really, we shouldn't have had to do all that work. We should go right back up here and note that row 3 is a multiple row 1. 2 times 2 is 4. 2 times -1 is -2. 2 times 6 is 12. So if one row is a multiple of another row, we know that the determinant is 0 right up front. So we would have saved ourselves some work had we noticed that.